Section 8.4 is improper integrals. So let's take a look at what this means. Here's our definition. Go ahead and write this down, and then we'll talk about it. So pause and write. Okay, so integrals with infinite limits of integration are improper integrals. Take a look at this graph. This function, as it goes towards infinity, approaches zero but never gets there. So there's never a place where this will close off. So to find the area goes on forever and ever and ever. To handle that, we use something called an improper integral. So if f of x is continuous on some value a to infinity, that would be this picture here, then the integral from a to infinity is found by taking the limit of the integral from a to b of the function as b approaches infinity. Same thing true to the other side. If we start at negative infinity and go to a value b, then the integral from negative infinity to b is the limit as a goes to negative infinity from a to b. And if it's continuous from negative infinity to infinity, we pick a point in between and examine two improper integrals. We'll do one of these examples as we go through. All right, so let's take a look at a couple of examples and just work through this. So 1 over x is the function that looks like this. And if we go from 1 to infinity, we don't have a closing point for our area. So this is an improper integral. So we're going to rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. So we're going to handle this part just like a regular integral. We're going to take the antiderivative, the limit as b goes to infinity of ln x evaluated from 1 to b, which is the limit as b goes to infinity of ln b minus ln 1. Now, ln of b as b approaches infinity also approaches infinity. So this becomes infinity, ln 1 is 0. So since this area approaches infinity, we say that the integral diverges. It does not have a value. It gets bigger and bigger as we go. Now, it seems that that would always be the case, but it's not true. Let's take a look at another one. Here's the integral from 1 to infinity of x times e to the negative x dx. So again, we have to set this up with a limit as b goes to infinity of the integral from 1 to b of x times e to the negative x dx. So I'm going to find an antiderivative here. I'm going to need integration by parts. So if u is x and du is dx and dv is e to the negative x dx, then v is negative e to the negative x. Using my integration by parts, I'm going to rewrite this as the limit as b approaches infinity of x, negative x e to the negative x minus, but I've got another minus sign here, so it's going to be plus the integral from 1 to b of e to the negative x dx. This can be integrated on its own. So I've got the limit as b approaches infinity of negative x e to the negative x minus e to the negative x, and all of this evaluated from 1 to b. So again, plugging in my values, I'm taking the limit as b approaches infinity of negative b e to the negative b minus e to the negative b, all minus negative e to the negative 1 minus e to the negative 1. Yep, and that's it. So now I have this whole piece, and I'm going to write it this way. All right, so that's 1 over e and 1 over e. I should have done that as well. And I want to evaluate this as the limit as b approaches infinity. Both of these pieces, e to the b gets bigger much quicker than b or 1 does. So both of these go to 0, and my answer is 2 over e. So this, although we are approaching infinity and there is no closing point on my area, the area, excuse my voice, the area under the curve does approach a concrete value of 2 over e. Okay, let's do another one. I'm doing several examples so you see several different types. Okay, to integrate this, we need to find a point in the middle because I need to break this into two integrals. So I'm going to break this up, and 0 is a typical point to use unless there's some specific reason in the function not to. And I'm going to do the 0 to infinity of 2 over 1 plus x squared dx. Now, both of these need to be integrated individually with limits, but let's go ahead and say that we are going to take a, the first part, I'm going to do the limit, and I'm going to use a approaches negative infinity from a to 0 of 2 over 1 plus x squared dx. We'll do this part first. So this is 2 tan inverse x. Remember your tan inverse function? So it's the limit as a approaches negative infinity of 2 tan inverse x evaluated from a to 0. So it's going to be 2 tan inverse a minus 2 tan inverse of 0. Tan inverse of a, whoops, I did this backwards. That's 0. And that's a. So tan inverse of a, tan inverse of a as a approaches negative infinity means what angle would give me a tangent value of negative infinity. That happens at negative pi over 2. Tan inverse of 0 would be 0. So I have negative 2 times negative pi over 2, which gives me pi. We do the same thing for my second one. I'm going to take the limit as I'm going to use b here. B approaches infinity of 0 to b, 2 over 1 plus x squared dx. Again, that's going to be the limit of, as b approaches infinity, of 2 tan inverse x evaluated from 0 to b. So that would be 2 tan inverse b minus 2 tan inverse x. And using the same process I did before, I'm going to do 2 times pi over 2. That's going, oops, I'm sorry, that was 0. That's going to be 0, and I get pi again. Adding these two together, my integral from negative infinity to infinity of 2 over 1 plus x squared dx will equal 2 pi. Adding together my two parts. All right, one last thing to look at. improper integrals with infinite discontinuity. So, again, copy this down. Integrals of functions that become infinite at a point within the interval of integration are improper as well. So if f of x is continuous on a to b, then the integral from a to b of f of x dx is the limit as c approaches a from the right, because a is your left endpoint. So in other words, at a, I might have a vertical asymptote. So I can't integrate to a because, again, there is a gap here. So I approach a from the right and go to b, and let's say b is an endpoint. Same thing holds true if my asymptote is on the right. I would approach b from the left. And if f of x is continuous on the union of these two, then I would do a to c and c to b, again, using limits as we approach c. Let's do one of these. All right, so at the point x equals 1, we have a vertical discontinuity. So it's continuous from 0 to approaching 1 and approaching 1 to 2. So I can split this integral into two pieces. Each one of these is going to be improper because there's a vertical asymptote at 1. So each improper integral. So starting with the first one, I'm going to use a value c, which approaches 1 from the left.